Hello, this is Dr. Scott Carroll. I'm here to talk today about one of my favorite topics, which is the teen brain. This is a very popular talk which I've given to um, at numerous conferences around the country, and it's probably my most requested talk after or on par with the one about surviving manipulative people, which you can also look at on my either my website or through YouTube. YouTube. Um, so, one of the things we're going to talk about today is sort of how the teen brain is different from the adult brain, and more importantly, how does it work differently? So, many people think when they see the teen brain that it looks something like this, where, you have the love lobe here in the front, which basically takes up a huge portion of their brain. And then you have other parts like the rebellion center, which is still fairly large. Um, you also have pieces like, the judgment gland, which is unfortunately quite small. And then you have things like love for parents, hate for parents, the yin and yang of the two. And of course, in the back, they have all the answers back here in the back of their brain. And down here at the bottom, they have this tiny little section that's even smaller than their judgment gland, which is memory for chores and homework. So I love this slide, but it's not, obviously this is not real, but, sometimes it seems like this is the case. But let's look at what the brain really looks like. So here we have, on the left side here, we have the brain basically cut in half. So that's what it kind of looks like on the inside. If you got rid of the blood, it would look mostly kind of pinkish with some white parts. But let's focus on the outside instead. So let's focus more on the right for a moment. And first, you're going to have, starting in the rear. So this is the back, and the back of your head is the occipital lobe. That's that little purple section right there in the back, which is right above the cerebellum, which you can kind of see on when the brain is sliced in half on the left. So the occipital lobe is essentially our visual centers and where we see. And now what we have here, the temporal lobe, which is in green, this is the part of our brain that kind of sits just underneath our ears and cheekbone. And the temporal lobe specializes in sound, so auditory processing. But on the underside, it has a lot of inputs from our sense of smell. So there's quite a few things related to smell and sound there in the temporal lobes. Now, up here on the top, this pink section is something called the parietal lobe. Now, the parietal lobe is what we think of as an integration center. So it takes inputs from lots of different places to produce answers. So on the sort of front edge of it, that front sort of band, right, that basically touches that, the yellow of the frontal lobe, is your sensory input from the body. So the whole body is literally mapped out in that strip that runs top to bottom there and touches the frontal lobes. But the parietal lobe takes information from that, and then it takes information from the occipital lobe, so visual inputs. Then it takes auditory and smell inputs from the temporal lobe, integrates all that information, and then passes it to the frontal lobe to make a decision about what to do. And of course, the frontal lobe is right here, in the front. You can see right there. So that's sort of right behind our eyes. And this is where sort of we do our higher order thinking with. Our personality is largely based here. So there's quite a few things. The frontal lobes are quite important. So now let's take another look at the brain. Again, we're going to do that cut down the middle. Sort of if you're just looking at somebody and you just cut them right into two equal mirrored halves. And again, we'll go through things in the same order with the different lobes of the brain. So back here in the purple, again, is the occipital lobe. You can see that right there with the green arrow. And then the temporal lobe, which is in a dark green here, and it's kind of underneath the brainstem, which is there in the gold, and you can see it pointed out by the red arrow. And again, on the top, this is that pinkish color is the parietal lobe. So you can see it again. That's what it looks like on sort of in the middle. And there in the blue, so instead of yellow like last time, the frontal lobe is now blue. Now you do see this sort of purple area, the cingulate gyrus, that's sort of wrapped around that white and gold brainstem. We'll talk about that next in the next slide, because that's a really important area as well. So here's another picture. Again, we're looking at the brain from sort of the side again. But the other really important structure in the brain, or large structure, is called the limbic system. And you see it there on the right, sort of deep inside the brain in gold. And it sort of wraps around that brainstem. And so there you can see it starts there in the frontal lobes, and then wraps around the top until it comes back to the occipital lobe in the back. There with the blue arrow, and then it comes around wrapping around through the temporal lobe, forming important structures like the hippocampus. They're indicated by the purple arrow. The hippocampus is particularly important in memory and learning, so that's a really important structure there. And then it continues back again forward to the tip of the temporal lobe, where it reaches the amygdala. Now the amygdala, or Latin for almond, is the very small little part of the brain that's involved in the fight or flight response. So so you can see that we get the limbic system includes a lot of emotional processing, and so learning, memory, also fight or flight, so anxiety. These are all important things, as well as judgmental inputs. All right, now let's move. Now that we've kind of looked at the bigger pieces, let's look at the smaller pieces. So we're going to look at the structure of a neuron here for just a moment. The neuron, you can see this here. So this is sort of, the typical textbook neuron you may remember from college biology or, high school biology. And you can see the nucleus there, the cell body with the nucleus in the center indicated by the red arrow. That has all the DNA and mitochondria and all the different important functions of the cell. And then up here, branching out from the cell body, is something called the dendrites. And so these are sort of short connections where other neurons synapse or connect to the cell body through that. And so they're kind of like the ears. They receive information from other neurons and other sensory organs. The next piece I wanted to show you is this long piece kind of wrapped with these little purple sections. This is called the axon. The axon is this long projection that goes from the cell body all the way to the target, which could be another neuron, it could be an organ, it could be your heart, it could be a muscle cell. So there's a long connection there. And the axon can be incredibly long. So if you think about it, so the muscles in your toe, in like your big toe, the cell body is actually sitting up in the middle of your back, and so that axon goes all the way from the middle of your back all the way down to that little muscle in your toe, and vice versa. The those pain receptors, when you stub your toe, the cell body is sitting all the way up in the middle of your back, and that axon runs all the way up your leg. So they can be incredibly lengthy. And this structure is the same for other animals, including, whales. So, some of these can be really incredibly long. And so that's why it's very important for these cells to have something to help them. And, sorry, you can see there in the red that's the target. Which is, another muscle cell or organ or so forth. But what's really important for maintaining this axon is this myelin sheath. Now the myelin sheath is it's actually created by another cell, and another cell sort of stretches itself out and wraps itself several times around that axon. And you'll have like one wrap in each section. So each little purple rectangle indicates a wrap, and you can actually even see that really small cell body with a little dark dot in the middle there on some of those myelin sheaths. Now the myelin sheaths are mostly made of fat, so they tend to have a whitish color, and they have little gaps between them, and the gaps are really important because normally when a neuron sends the signal down the axon, you have little channels that go all the way down, little channels for ions like sodium and potassium and so forth, and that sort of change. So it's sort of like as it goes down the street, it goes from one it goes from like one channel to the next. So what we call a spreading depolarization. So just some fancy words, but essentially it's like an electrical signal. So it does not go the speed of light, not like the way it does or close to it in, say, like a fiber optic cable or a coaxial cable. So it's much, much slower. And so what you think of it is that when you don't have the myelin sheaths, and there are unmyelinated nerves. One example is like hot or cold on the toe. I don't know if you've ever done this, is that if you actually put a piece of ice, you don't feel it right away. There's a split, it takes a little bit, whereas like someone pokes you and it's like instantaneous. So there are different transmission speeds, and dull pain is considered one of those slow transmission speeds because it's an unmyelinated neuron, so it goes very slow. And so I compare it, now in the case, however, of when you have myelin, what instead happens is the signal literally jumps over the myelin sheath, and essentially it's jumping from gap to gap to gap. And I'll show you. So like this. So it jumps from one gap to the next gap, just like that. And so what that means is because of that jumping effect from gap to gap, you get a much more rapid transmission of the signal down the axon. And so the way I compared it, you might even think about it like if you're just going down an unmyelinated axon, it's like driving across town, literally block by block, with a stop sign at every block, so you can do it, but it's slow and, it takes quite a while. Whereas in the case of the myelin sheath, it's really like hopping on the interstate, and the gaps are just the exit ramps. So you're literally just like virtually like jumping from, exit ramp to exit ramp to exit ramp. So much more rapidly in the terms of the speed that you get around that you can get around town. So now let's look how how this myelin is laid, the cell bodies in the myelin are laid out in the brain. So here's a picture of the brain looking more kind of from the top, looking down on it. So if you can see here from sort of the little small image that the brain, if you sort of cut the skull off at the top, sort of at a little bit of a down angle, and this is from the side, and you look down on the brain, this is basically what you see here in the larger picture. And so as we've been talking about, the myelin is mostly made of fat and is therefore a white color, just like fat. And so you can see these inner parts of the brain essentially look white, and that's due to the high level of myelination on the axons in this area. And you can see that the axons literally cross from one side to the other and one section to the other, and because you're spanning fairly significant distances relative to the small size of the cell body, which you would need a microscope to see. Now, in the case of the cell bodies, they actually form the gray matter. So where the synapses are, where the dendrites and synapses and cell bodies are all in this gray matter. Now, I know in the picture it looks pink, and that's just because when you actually preserve a brain for autopsying, you use formaldehyde or some other substance, and it typically makes the brain look gray. So the gray matter of the cell bodies actually look more grayish, whereas in the live brain they actually look more pink. But you can see that it's spread all around the outside of the brain, inside the folds, with the myelin and the white matter on the inside. And that's because literally the cell bodies are on the outside, and then the axons project, into the white, where the white matter is to, some other part of the brain. So the white matter tracks here. Now this is an image created from something called tensor diffusion imaging. So essentially what we're doing is we're tracking the diffusion of water molecules with an MRI, a special type of MRI machine. And so we can literally see how the tracks are laid out in a living brain. So this is actually from someone who is alive. And so let me kind of orient you for a moment here. So first, you can see that kind of blue. It starts off green and then it goes blue. That's the brain stem. So very dense white matter connections going that go on to form your spinal cord just there at the bottom of the picture. Then the next piece right here, this little section sticking out, kind of that's green sticking, and this is posterior. That's your cerebellum, which is very important for coordination of movement, thought, speech, all those kinds of things. And then if you look at like this is the frontal lobes here in the front. So the person is facing to your left in this picture. But you can see how neatly laid out these white matter tracks are and how well organized they are. And this is actually one of the big clues about what's wrong in schizophrenia. We know that in schizophrenia, especially the paranoid types where people hallucinate a lot and are paranoid a lot, these white matter tracks are not well organized like this. And so that's a big clue as to what causes schizophrenia, which we, by the way, we still don't fully understand, but we're working very hard on trying to figure this out. All right, now let's take another look, same brain. Now this is the front view, looking, so the person is basically facing you. And so let me kind of orient you here to some of the basic pieces. So see this purple section highlighted by the yellow arrow these are the large connections that go from the two halves of the brain, so it's on both sides, and they go down and then meet there at the base to form the brainstem and spinal cord. So this is actually these large white matter tracks that are going down to form the spinal cord. So like things like the nerve signals to move and sensory input of like pain, temperature, things like this are all going up and down this track. Next we see here at the bottom in this kind of red and yellow color what this is. This is literally the part of the brain where the white matter tracks cross over to the opposite side. So you probably have heard that the left side of your brain controls the right side of your body, and vice versa. And that's because of this big section here in red where the white matter tracks literally cross over. And here what you see there is that red piece kind of growing, that heavy section going across the brain. Again, that's the big piece of white matter tracks known as the corpus callosum that are crossing to connect the two halves of the brain. And so that's a big, very intense, very large, well-organized white matter tract there. So now that we kind of know how the white matter tracks are laid out, one of the things to talk about, the next thing to kind of talk about is how the neurons are deeply interconnected. And so you can see on the left, starting with the left, you see the newborn where they're just starting to branch, forming dendrites and axons and things like that. And then even by just a month later, they're much more developed. And by 6 months there in the third picture, you can see they're really starting to connect. And by 2 years of age, the neurons are densely interconnected with each other. So you can see that these interconnections grow and form very rapidly. Now, the other thing to say is you can see that the structure of the neurons, and the picture on the left just kind of shows you what the complexity of the structure of an adult neuron. And we start off with very simple neurons as babies, and then we reach full maturation. But then as we age and we get older, the neurons lose their density and interconnectedness. And so literally we kind of go out the way we came in. So, the old joke about little brains, so whether you're young little brains or old little brains, they're very similar. That's why one of the reasons, even though I'm a child psychiatrist, I actually feel pretty comfortable with geriatric psychiatry because they're just so similar, believe it or not. But anyway, one of the things to say is that, as these neurons become more complex, you get a massive increase in connection between about 7 years of age and 11 years of age. And so there's actually kind of if anybody remembers, there was an old game show called Are You Smarter Than a Fifth Grader? And so what this does is these massive overconnections between the neurons literally allow like fifth graders who are 11 to massively remember just raw facts and data. Okay. And so if you remember the show, it was always questions like name the 50 capitals of the states and blah 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 blah. And so, the whole game is actually rigged to basically make the adults look stupid because it plays to the cognitive strengths of an 11-year-old. Because there are things they're better at remembering raw facts than an adult. Now, obviously, adults are much more functional than an 11-year-old, so just having facts is not sufficient, and it's more what you do with the facts. And besides, as adults, we just look it up. We wouldn't waste the brain space to try to remember it all unless it was, something we used fairly regularly. The next thing to be aware of is that starting between 12 and 14 is that the brain then takes all this extreme connections and pairs it back to something more useful, which is called pruning, and which actually has to do with language a lot. So if you think about it, the way the brain is built is actually more like carving a statue than building a house. So if you think about it, the brain overconnects itself, kind of like just the block of granite, and then the brain prunes back the unuseful connections or the parts it doesn't need, and what you're left with is the statue. So just in the same way as the statue, you chip away at all the stone you don't want there to reveal the image. It's not actually, you don't actually build a structure. It's more like you have kind of a block and then you carve away at it and remove. And the brain is actually constructed the same way. And this intense pruning between 12 and 14 has a lot to do with why teenagers are so irritable around this age, why they're so emotional, but we'll get more into that a bit more in a bit. Now, after 14, the pruning slows down, and that's when the brain, once the brain knows what sort of long axons are going to be left, the brain then starts to myelinate them. Essentially, you start wrapping those, cells around it, those fat, wrapping that fat around it to increase the transmission speed. And that's where, and this is when, starting at 15 is when you start to get these long white matter tracts begin forming. Now, as we mentioned, the myelin makes these long white matter tracts, transmit the information much more rapidly. And just to give you a sense of how much more rapidly this is, so if you think about it, the myelinated tract, the myelinated tracts are basically like fiber optic cable. They're extremely fast, whereas you compare the unmyelinated fibers, it's basically like dial-up. And so if you remember, I'm old enough, unfortunately, to remember this. We remember the old modems, telephone modems, and you literally, when they first came out, you'd put the handset, you'd use your regular phone and put it on the handset, and it would go, it'd make all those weird sounds, to transmit, the information. And you can also remember they were incredibly slow, and man, if you had, 49K baud, you were like really cooking, but if somebody picked up the phone in your neighborhood, or it rained, or anything, that it would slow down to like 2 baud, and, now we talk about, megabits and gigabits per second as opposed to kilobits. So, with that fiber optic cable. So much more rapid. And what this means is that this rapid myelination of the long matter tracts allows the brain to communicate, much more rapidly. And so what happens is that, adolescents, because they don't, up until 15, they don't actually have really much myelination in their brain outside of their motor system, so that they can move. 15-year-olds can be pretty coordinated, but in terms of especially their frontal lobes, they really have very little myelination in them. So what it means is the brain, the nerves cannot send the information like literally one side to the other. Because it would take too long. So essentially what you get is localized processing of information versus the way an adult processes the information by sending it all over. And so here's a picture. Now I live in New Mexico, and so I'm actually in Albuquerque, and you can see Santa Fe there with the stars just, a little bit north. I mean, that's about an hour drive. And so, That's kind of like if you 2K baud, you can maybe get to Los Alamos, or if you're really if the weather's great and you got that 49K baud, maybe you can get down to Las Cruces there at the bottom, or one of the other smaller cities. But you're kind of limited to your local area. Whereas in the case of an adult, they can send the information literally all over the brain. And you can see here, this is actually a map of looking at all the airplane flights around the world, and you can see how dense they are, Europe and U.S. and how quickly. And so the point is of this slide, of this picture, is to actually show that in the adult brain will literally send a thought back and forth from one side of the brain to the other several times in just milliseconds before you get that output. And so whereas and because of that high speed of transmission, the brain, the adult brain is able to do that, whereas the adolescent brain can't, and so it has to process things locally. And that's why that myelination is such a critical phase of growth in terms of brain development, and it doesn't even begin until approximately 15 years of age. So, which is kind of interesting when you think about the fact that your IQ test is basically done in 15-year-olds. So this is kind of why an IQ test is just not a particularly good way of assessing full cognitive function in a person. Because, anybody knows the difference between, how functional a 15-year-old is versus a 50-year-old. So they're, quite night and day. And so you can see a big difference. And so that myelination really starts to take place from 15 on. And so now the scary part is a lot of it doesn't even occur till 18 to 24. So it may start at 15, but a lot of it doesn't occur until much later. And the other problem is that the myelination starts in the posterior with the occipital lobe. And guess what the last area to myelinate is, which is, of course, the frontal lobes. And so that's why your thinking and your judgment are literally the last parts of your brain to come online. And the whole point of this is that judgment, emotional stability, and impulse control really don't become meaningful till about 25 years of age. Females can do this a little earlier, maybe 23 at best, but really 25 for most adults. And we've long known something happened with judgment and emotional stability because car insurance rates have long the statistics just bear out the fact that adolescents and people under 25 are much more dangerous drivers, have far more accidents. And then once you turn 25, your car insurance rates dramatically drop. And I remember this because I had a sports car back then in my early 20s, and somehow I didn't wrap myself around a tree, and not that I, didn't from the lack of trying. I had many close calls, and it's kind of a miracle I'm sitting here talking to you. But, I remember once I turned 25, my car insurance rates dropped, and just that need to drive like a banshee just kind of evaporated. It's very interesting because I remember it clearly. And you can see this, hence the picture on that left. And yes, that red car is a Ferrari, and someone just drove it into a pole. And so you kind of see the kind of silly accidents you get into as an adolescent. So what does this all mean? So in this case. So one of the big problems is that teens frequently, because of this lack of myelination, especially of the frontal lobes, they have this black or white thinking, which is sort of yes or no. They don't tend to see shades of gray. And as we know as an adult, when are things black and white in the real world? They almost never are. And so adolescence, and when I mean adolescence, I mean up to 25. So, anyone basically 15 to 25. Which we define adolescence as physical maturity but neurological immaturity. So it's that weird phase where the body's developed but the brain's not. And so anyone who works with adolescents will know they just, they miss complexity, they miss shades of gray, they miss some of the obvious pitfalls of situations. And so, they just often kind of think in very absolute terms about things, and so they miss the subtleties, if you will. But the other thing is that unmyelinated neurons are also kind of like that modem that we talked about when we talked about how it could if everything was perfect, it'd run at about 49K baud. But when anything happened, rain, someone picked up the phone, whatever, it would really slow down. And adolescence, the unmyelinated brain of adolescents is similarly very sensitive to environment, particularly stress. And so if they're sleep deprived, or if they're just under a lot of stress, or even just something simple like peer pressure, it really affects their ability to think clearly. So if they're calm, or they're asked about something hypothetically, they can be very rational. But the minute you put them under stress, they become confused, they become overwhelmed by these emotions and impulses, and they literally can't think clearly. And so there are all kinds of reasons, or implications of this fact. But one thing to, just be very clear is that you can really, if you stress a teenager, you can just about make them do anything, like shoot a gun at somebody and kill them, like, our military, likes to do. And there's a reason why the military likes to draft people at 18 and really doesn't want you when you're 25. Because then they have to explain to you why you need to kill that person. So there's a reason why the military likes to draft at 18 rather than 25. And so, and this sort of difficulty with thinking clearly under stress can be so profound that adolescents can literally regress to the point that their thinking becomes very childlike, almost like a preschooler, where it becomes magical, and they really have a hard time distinguishing, reality from fantasy. And so if you stress a adolescent enough, you can really just mentally break them down, and make them, really function and think like a preschooler. And so, it's very important to realize that how sensitive they are to stress. So let's use some examples and look at how this comes up. So common situations with teens. They often have very unrealistic expectations for life, or they believe they are magically protected from danger. And so that's a really common problem. So, again, notice that magical thinking is very common. They can magically deny a problem even exists, and avoid asking for help. This is kind of the case of, people often wonder, like, how do these girls, teenage girls who give birth, like, in the bathroom, not know they're pregnant? And this is actually why, because they're so stressed by the situation that it breaks them down mentally, so they literally are thinking like a preschooler. Or sometimes they just want to deny something existed. As a result, now the good news is teens do have a backup plan, and so there is at least one bright spot in all of this, which is that they will go to a trusted adult and say, just tell me what to do. And that's the one time it is okay to tell a teenager what to do. Otherwise, you don't tend to get real good reactions from them, which we'll talk about in the next slide. So let's talk about some techniques for dealing with stressed teens. First thing, slow down. They're just like a toddler. You speak slowly to a toddler. You don't get too complicated. Use very simple, concrete examples. Now notice I'm talking about how you speak. I'm not saying you speak to them in baby talk. I'm not saying you speak to them like they're a toddler, and certainly don't tell them that. They tend to react very badly to that. But you want to just kind of keep it simple, keep your voice calm. You don't want to stress them out more. Keep the language simple so they can process it. Other things that also are helpful, being neutral. So not taking sides about things, not getting angry or upset with them, not telling them that, what they want to do is totally crazy and they're an idiot. Obviously that goes over really well. And also respect that they have to decide for themselves. Which is sort of like, it's like, look, hey, I don't know, but, might want to think about this, but it's your decision. And so, and just kind of pointing little things out to them, but, being very respectful that, it's up to them about what they do with that. And a lot of times you can get, that can calm them, help them kind of recognize some of these pitfalls that they're missing in their own thinking. Another technique I like is called playing Columbo. And this, anybody remember the old TV show, I'm totally dating myself here, of where, I think it was Peter Frampton, I believe, who did it, but it was basically a detective show, and Peter Frampton's character, whose name was Columbo, hence the name of the show. He always looked like he just rolled out of bed and messy hair, and he had this like old trench coat on, and he just kind of came across as like this simpleton, like he just didn't know anything, and like and he'd always come in and he'd be questioning the killer, and he'd be like, now tell me again what you did after you found the body. What was it again? And he would act like he was just the dumbest thing on the planet. But he was so, but that act of seeming so dumb and unable to understand, often got the killer to talk more and explain more and try to explain, and they're just trying to help him understand what happened, that he would then catch them in some kind of lie, or catch them in some kind of logical impossibility. One of the way you do this is you often ask, with a teenager, you often ask leading questions, and this is here where I'm talking about how much you're going to make a month and how much does the apartment cost. This is for, like, say, a teenager who wants to move out, and I'm going to move out with my girlfriend, and and I'm going to get a job at McDonald's. Not that McDonald's is bad. Most of us have worked for McDonald's at some point, but then they somehow think that they're going to make enough money at it, that they're actually going to be able to get a nice apartment, and so and sometimes it's like by just asking leading questions to get them to think about what's going on. So it's like, okay, so how much are you gonna make at McDonald's? It's so much an hour. How many hours are you gonna get? Okay, in a week. All right, let's add it up. And then it's like, and don't forget about taxes. So how much are you gonna actually take home at the end of the month? Oh, okay. And so you're going to take home, $500, a week, and your apartment is what, $2,000 a month. It's like, when you add it up, they're like, oh, and they start doing the math and they say, oh, that's not going to work. So the point is, you don't just criticize what they're doing, even if it doesn't make any sense, is because the thing is, the answer, but that doesn't help them. It's more important that they learn the answer. And so by guiding them through, just taking these steps and making them think through the process, just asking really good questions in a non-threatening way, can help them lead to saying, and then, they're going, oh, I'm only going to make $2,000 a month, and my apartment's $2,000 a month. I'm going to have to get a much cheaper apartment. Yeah. And so they can start to figure it out. So, and obviously we could spend all day talking about this stuff because, these are just some basic points. But, gives you a sense, if you can do nothing else other than sort of recognizing that teenagers just can't think clearly when they're stressed, doing things to kind of calm them down, kind of get them focused on other things, being neutral, being non-reactive, respecting their right to make decisions within reason about things, and then asking just these good leading questions of like, how's that going to work? So they start to think about what's going on. All right. Well, thank you for your attention. I do have some other things that may be of interest from you. I did write a book called Don't Settle, How to Marry the Man You Were Meant For. Yes, I wrote a trashy dating book. It's available on Amazon. And I actually even though it's trashy, I won some awards. So I've had a lot of people feel like it was very successful, and I have a growing list of women who have met the man of their dreams. Well, maybe I shouldn't say dreams, because their dreams are often magical, but a good man that they have an excellent marriage with. So if you're interested, check it out. You can also see more content like this on my website. I have articles about everything from relationships to parenting to other mental health topics, like working with manipulative people, and as well as things about bipolar disorder. You can also follow me on Twitter, Instagram, and Facebook at Scott Carroll MD. All right, thank you very much, and I look forward to speaking to you again soon.